Well, hopefully that last section on limits went well for you. So today we're going to talk about another important concept, and that's continuity. And continuity intuitively is fairly easy to understand. You know, if you're drawing a curve, you don't pick up your pencil, so there's no holes or gaps or breaks or jumps in the graph. But in order to prove that it's continuous, we have to talk about the definition of continuity. And in order for a function to be continuous at a point in its domain, then these following conditions have to be met, and there are three of them. And the first one is that the value of the function at c has to be defined. So you have to be able to plug in the value for c and then come up with an output value. So that's the first condition. The second condition is that the limit as x approaches c of the function must exist. Okay, so remember when we talked about the limit? So in order for the limit to exist at c, so let's say this is c, this is any x value, and let's take maybe a function that looks like this. So we see here at c that the limit does not exist. So it is defined at c, so it hits the first one. At c, it's this, whatever this value is up here. So it is defined, but we go down to the second condition and we see that the limit does not exist. As we come in from the right on c, it's one value, and then as we come in from the left, it's another value. So here would be an example of discontinuity. So it breaks the second condition. Okay, the third condition is basically that those first two are equal to each other. So we would have to say then that the limit as x approaches c of the function, so the value we get for the limit at c has to equal the value of the function at c. So an example of where that would not occur is maybe we have, this will be c here, maybe we have a curve that's going along here, but at c there's an open circle. Okay. So in order for it to be continuous then, the limit at that point would have to equal the value of the function. But let's say that the value of the function is this number right here. So we can see that that value is not the same thing as the limit. So this would be an example of how number 3 would not, this condition would not be met. And so those are the three things that we have to look at. Is it defined? Does the limit exist? And then do those two things equal each other? Okay. Continuity of polynomial functions. Well, we know that a polynomial function is a smooth, continuous curve. So here might be a cubic polynomial. We could have a quadratic parabola. We could have a fourth degree. So all polynomial functions are continuous at every point. Okay, because in polynomial functions there is never a gap or a hole. So they are continuous over the set of real numbers. Rational functions, however, are only continuous at points that are in their domain. So let's take the parent function f of x is equal to 1 over x. Okay, so that rational function looks something like this. And the domain of this rational function is all real numbers. X is not equal to 0. Okay, so it is defined from negative infinity to 0. So on that interval then, it is continuous. It is also defined from 0 to infinity. And over that interval, it is also continuous. So it's continuous on the intervals it is defined for. Discontinuities. Well, we have two kinds of discontinuities. We either have removable or non-removable. A removable discontinuity would be a curve that basically has a hole in it. So let's say we have this function here, and at this point right here, we have a hole in it. Okay, so it would be discontinuous at that point, but it's a removable discontinuity because all we would have to do is define the function for c, and if we told it that it's equal to this number right here, then we could make it continuous. So that's an example of removable, where all we have to do is define f of x at c. Okay. A non-removable discontinuity then would be something like that last curve. So if we have this curve here, and we know that it's discontinuous at 0, well, even if I defined it, even if I said at 0, the value of the function is going to be 0, well, it is still not going to be continuous because I still can't draw it. So just defining it there doesn't help. So this is an example of non-removable discontinuity. Well, to have continuity in an endpoint then, you still are just drawing the whole graph. Even though the graph might not go on and on, we can still say it's continuous on an interval. Let's just take the function f of x is equal to the square root of x. Okay, and we know that that curve looks something like this. So it's defined from 0 to infinity. And on that interval then, it is considered to be continuous. So we don't have to look at the limit at this endpoint here from both directions. So since we're only defining it where x is greater than or equal to 0, then we only have to look at the right-handed limit. So as we're coming in then on 0 from the right, then the value of the limit from the right is the same thing as the value of the function at 0. So we would say then that this is continuous. And it's continuous on the interval from 0 to infinity. Okay. So it is possible to have continuity then on a closed interval. So here would be another example. Let's say that we have this graph here, And let's go up here. Come on. And then we'll have a ray coming off this way. Okay, so we're going to take a look at a piecewise function here. And let's say that f of x is equal to x plus 2 if x is greater than or equal to 0 and less than or equal to 4. So I'm going to go over here, 1, 2, 3, 4, and actually I'm going to change this to a closed circle. So I'm just going to look at that. And then I'm going to come over here and maybe just look at this here. I'll add that in here. So we'll go over here. And we know that f of x is going to equal to 2 when x is in between -2, oh, I didn't leave myself much room, and 0. Well, at the endpoints, we just talked about on that last one, so we can say it's continuous here. So we just have to talk about the left-handed limit as it's approaching the 4, and we have to talk about the right-hand limit as it's approaching 2. So the only other thing we have to look at is what's going on here in the middle at the 0. Okay. Well, as we are approaching 0 from the left, the value, the limit, it's getting closer and closer to 2. And as we come in from the right, it's getting closer and closer to 2. So the limit exists, and the limit is 2. And then the value of the function at 0 is 2. So because all of those things equal right there, then it is continuous on that closed interval, even though we have kind of not a break, but a bend in the graph. Okay. Well, hopefully that kind of gives you a good start to how we're going to prove that functions are continuous. And we will work some more on that in class. All right, thanks.